right, continuing on with our quadrilaterals, we've worked on parallelograms and all the various properties of a parallelogram to this point. We're going to add an extra property to make parallelograms into rectangles in this section. Definition of a rectangle is a quadrilateral with 4 right angles. So first, let's talk about why, if we know something is a rectangle, we also know that it's a parallelogram. Why does it fall under that same umbrella? So if we can show that the sides of a rectangle are parallel, then it will have that same property and be a type of parallelogram. Exercise 1 does just that. So we have a rectangle drawn here, and we're giving a justification for why line M must be parallel to N and why line P must be parallel to Q. So one way to say that is that the corresponding angles on either side of these lines are equal. Since we have 90-degree angles all around, that can force them to be parallel. We also could say that the same side interior angles between these two conjectured parallel lines are supplementary because they're 90 each, and so they're going to add up to 180 as well, like they should. So a couple of different ways we can prove that. So we can say definitively that if a figure is given to be a rectangle, it also has all the properties of a parallelogram. All right, so in exercise 2, given rectangle MNPQ, do the following. And so we can get some tracing paper out and do part A, or you can use a ruler, do whatever you need to, just to show anecdotally that in this diagram, NQ and MP are the same length. They should come out that way. So to give a proof of it, what we want to do is pick out a couple of triangles in this diagram that contain the full length diagonals, which means I don't want any of the 4 smaller triangles because none of those span the entire length of a diagonal. So what I'm going to choose instead is triangle QMN, which is this upper left triangle, if you will. If you can follow, you actually have to watch this and follow my cursor to see which triangle I'm talking about. QMN encompasses the entire length of diagonal QN, and then PMN encompasses the entire length of diagonal PM. And so I've got 2 overlapping triangles here that have, as one of their sides, a full length diagonal. So we know that because this is a rectangle, that was given to us, that angle M and angle N are right angles, so they each share an equal angle. They also both contain side MN, so that's a reflexive side. And because it's a parallelogram, well, all rectangles are parallelograms as we just discussed, then side QM and PN, being opposite sides, are going to be equal in length. So I have a side angle side proof here because I have the opposite sides, the right angles, and the reflexive sides. And so because of that, we know that those triangles are congruent, and therefore all their parts, including these full-length diagonals, are equal. So the summary of that is if we have a rectangle, then we have congruent diagonals, always. So that'll be a property that we use when we're talking about rectangles. If we know it's a rectangle, we can assume equal diagonals. So in rectangle RSTU, it's known that RS is 12 and ST is 5. I suggest you draw rectangle RSTU so that you can see what's going on here. But RS, being consecutive letters, is an outer segment of the rectangle. And ST is also an outer segment. It's the next one. And so to go from S to U is skipping over. That's a diagonal. And so these are going to come from a right triangle. And if you draw that rectangle, you will see how that looks. So we have a 5 squared and a 12 squared for the outer sides. Looking for the diagonal length, Pythagorean theorem will work to do that. All right, so on the next page, just as with parallelograms, we can prove something's a rectangle without knowing at first that its definition is in play. So in this diagram, what we know is that ABCD is a parallelogram and that the diagonals are congruent. So we know that AC and BD are the same length. And so first thing here is to try to prove that the overlapping triangles are congruent. So I'm looking at ADC this time, which if you can follow my cursor, you can see which way I'm looking, and also BCD, that's this way. Now I don't know that these are 90-degree angles because we are not given that it's a rectangle. That's what we're trying to prove. So what I do know is that the diagonals are equal. I do know that both triangles share segment CD, and I do know that because it's a parallelogram, opposite sides AD and BC are equal. So that tells me all I need to know in order to prove that these 2 triangles are equal by side, side, side. Okay, now angle ADC and BCD are the ones that are in question. That's down here and over here. Those are what would be the right angles if this is in fact a rectangle. Are they equal? Yes, because of CPCTC, they belong to those overlapping triangles we just talked about. So how can we use that fact to prove that they must also be right angles? Well, because it's a parallelogram, AD, if I were to extend AD and extend BC, those lines are parallel to each other. If two interior angles on the same side of transversal CD add up to 180, if those lines are parallel, they will add up to 180. And we just said that they're equal. So the only way two angles can be equal and supplementary at the same time is if they're both 90 degrees. Therefore, we have 90-degree angles, and the same concept would apply for these upper angles, and we do in fact have a rectangle. So if we know that an item is a parallelogram and we know that its diagonals are equal, it must be a rectangle. All right, and then exercise 5 here, we've got our quadrilateral plotted, and we first want to prove that it's a rectangle. So all we need to do is prove that the slopes of these segments make 90-degree angles. So if we calculate the slopes, you will see that EF and GH both have a slope of 2/3, and that FG and HE both have a slope of -3/2. So you can take a second to copy all that down. You can also use rise over run on the grid. That could be easier in this case, having a visual grid in front of you. And so because those slopes are opposite reciprocals, we can be sure that those are right angles. Second thing, to calculate the midpoints of the diagonals, so you might want to draw in segment EG and segment FH and try to find the middle, but we can use the coordinates to do so. Going from E to G, the midpoint is going to be 1/2 and 2. And from F to H, same thing, the midpoint is 1/2 and 2. We've seen this before. When two diagonals share a midpoint, that means that they bisect each other if they meet at each other's midpoint. And so the type of quadrilateral that has diagonals bisecting each other is a parallelogram. So that is another way to show that it's a parallelogram, even without having gone through the whole slope calculation. And in part C, finally here, calculate the lengths of diagonals of EFGH. So we just apply the distance formula. It turns out that EG is 13 and FH is also 13. So going straight across, this is 13 units. And applying Pythagorean theorem here, this is also 13 units. So why does that show that EFGH is a rectangle? With part B, so the idea here is if it's a parallelogram and the diagonals are equal, then it's a rectangle. So you have to have both. But once you know it's a parallelogram, if you also have equal diagonals, now you can be sure that you have a rectangle.